Hello, we are Team 4, and today we'll be discussing the optimization of a vertical farming system. Vertical farming maximizes space use efficiency by stacking crop growth, therefore allowing for more crops to be produced within a constrained space. The need for vertical farming is becoming more prominent, specifically in cities where space is an expensive commodity. While maximizing the use of space, vertical farming also requires more energy to pump water up to the crops in higher layers, so there are trade-offs between production per area and energy use. The objective function of our system is to minimize the energy consumption per crop. Our system will grow romaine lettuce. This is convenient because romaine lettuce has constant requirements for light intensity, water pH, and nutrient needs throughout its entire growth process. Our system will be an isosceles triangle structure that has rows of tubing on each side which hold the lettuce along them. The tubes will be connected on the ends as seen in the right figure. Water will be pumped to the top of the tube and will then flow along the bottom and throughout the tubing. This nutrient-rich water will be absorbed by the roots of the lettuce, allowing them to grow. The two sides of the structure are independent of each other, and therefore all calculations will correspond to one half of the system, demonstrated by width W. The system has three subsystems, which are crop production, electrical power management, and irrigation management. The inputs to our system are water flow rate, power to run the air conditioning, power to run the water pumps, and power for the lights. The system will then output the energy required per crop. The variables shared between subsystem 1 and 2 are the slope of the system structure, the length of the system, and the number of layers of plants. The variables shared between subsystem 2 and 3 are the volumetric flow rate. The variables shared between subsystem 1 and 3 are the total number of crops in the system. Finally, there are no coupled variables. Everything external to the system boundary, such as energy costs and food and safety regulations, are outside the scope of this project.
Subsystem 1 is crop production. Subsystem 1's goal is to maximize crops produced while minimizing the space used. We also have some assumptions that we made for the subsystem. For subsystem 1, the design variables include the angle of the base of the ground, the length of the subsystem, the number of layers. Also, the objective function finds the yield while taking the fraction of weight over the width to incentivize the system to be more vertical. These are the parameters and intermediate variables for the subsystem 1 based on the diagram on the right and the data from vertical farms that use romaine lettuce. Subsystem 1 side constraints include the number of layers, height of system, angle of structure, and length of the system. Subsystem 1 was optimized using the genetic algorithm from MATLAB since this is an integer nonlinear programming problem. Our 5 outcomes from using the INLP all come out to the same for our design variables and objective function. Subsystem 1 results in consistent values for number of layers, angle, and length. This also causes it to have the same yield. This is given that we use an upper bound for length since it is also determined by subsystem 2.
The objective of subsystem 2 is to minimize the amount of electrical power used to maintain the system. We divided the electrical power into power consumed by the AC, by the water pump, and by the lighting. And here are some assumptions listed. Our design variables are the slope angle of the system, the length of the system, and the number of layers. And the objective function is to minimize the total power consumption, which is the sum of all three components. We have a few general parameters and intermediate variables, namely the tubing outer diameter, the height between layers, the distance between each plant, the height of the first layer of the ground, and the maximum height of the system. And our intermediate variables are total height of the subsystem and half the width of the system. The air conditioning component has parameters of AC cycles per hour, temperature change per AC cycle, COP of the AC, specific heat of air at constant volume, and density of air. And the intermediate variables include volume of the system, which is assumed to be 3 times the volume of the vertical form, and power consumption of the AC system. The water pump component has parameters of pump efficiency, density of water, volumetric flow rate, and gravitational constant, and an intermediate variable being the power consumed by the water pump.
The lighting component has two parameters, the length of one light bulb and the power used by one light bulb, and the intermediate variable lighting power consumption, which assumes 14 hours per day of lights for the plants. Subsystem two's constraints include a constraint on total height of the system, on the angle of the system from the ground, the length of the system, and the number of layers. Subsystem 2 was optimized using the same method as subsystem 1, is also a constrained integer nonlinear programming problem, and it was done with genetic algorithm function in MATLAB. The results of this optimization are consistent over 5 trials and has a total power usage of 3.07 kilojoules per day times 10 to the third. The length was minimized. This makes sense as it reduces volume, which is directly proportional to the air conditioning power. The number of layers were minimized, which is also directly proportional to AC power and pumping power. And theta was nearly maximized at 80 degrees, which reduces width and volume directly proportional to AC power.
Subsystem 3 touches on irrigation management. The objective of the subsystem is to minimize the water use efficiency produced by our system. A few assumptions have been already mentioned prior to this, but a few new ones include romaine lettuce used as crop, warehouse size is not constrained, and crops are planted vertically. The two design variables identified for the subsystem were water flow rate and percent of water recycled. The parameters identified were water required per plant, total crops, maximum water recycle efficiency, water loss factor, and growth cycle duration. The intermediate variables of the subsystem are maximum water required, total water supplied per 70 days, effective water used, water lost by evaporation plus transpiration, and water absorbed by crop, all in liters.
The constraints of subsystem 3 were the water absorbed by the crops, and the side constraints are defined here as the percentage of water recycle has to be between 0 and the maximum efficiency, and then the water flow rate has to be between 240 and 720 liters a day. Subsystem 3 was optimized using constrained nonlinear programming by using the fminconf function in MATLAB. The objective function was to minimize the volume of water used per crop growth during the growth period, and this resulted in the optimized values and optimized solutions coming consistently. The water flow rate was minimized completely to 240 liters a day, which reduces the water flow rate, which is proportional to the water management. The percentage of water recycled was more minimized than maximized at 29.35% recycle efficiency, and the water use efficiency was optimized at 9.825 liters per plant over the 70-day growth period. The optimized inputs were repeated with each test, and the outputs it came up with were consistent with each test.